All right, guys, continuing right along, we'll look at Riemann sums now, which is where we're going to be working with a bunch of rectangles. Hence, why we've got this bell work. So if you've already done it, awesome. If not, pause the video and give it a try real quick, so you can see you got it right. It shouldn't be too much hard or too much trouble with this first one here. What we've got is we've got a series of 3 rectangles. This first rectangle here, right, is going to be a width of 2 and a height of 3. So that's simply going to be 2 times 3. Then we're going to add the middle rectangle here, which is going to be a width of 2 and a height of 4. So 2 times 4. And then we're going to look at this last one, which is a width of 2 and a height of 5. Putting that all together, we will get 6 plus 8 plus 10, or 24. All right. Now, what about a parallelogram? We got to remember how to do that as well. So this one is going to be our width times our 2 heights averaged together. So 4 plus 6 being the 2 heights of that parallelogram, where this would be 6, this is 4, and my width is 3. Okay. So then I can put all that together. I'm going to go 3 times 10 over 2. I do not expect you to write it in this many steps normally, but I'm doing it in lots just because it's the bell work and kind of some review. And so ultimately, our final answer is simply going to be 15 for the area of that parallelogram. All right, so let's get into Riemann sums for real here. All right, now there's a lot of reading that you can do if it helps you kind of understand it. But basically what we're doing is we're taking a look at this, which is the integral of f of x as a function represents the antiderivative, which is what we talked about before. We also call it indefinite integrals. This is because there's no bounds. We're just saying, find the whole thing. Whereas normally what we're doing is we have bounds. So you can see here I've put an A and a B on the top and bottom of this integral symbol. What this means is that we only want to know the area under the curve between A and B. So we're not looking for all of it anymore. Now we're just looking for a specific section. This is much more helpful, much more useful, something we're more likely to do as well, or in application problems. So a Riemann sum is a way for us to estimate this, because at the very beginning they had no idea how to find the area under a curve. And so we would estimate it. And so that's what we're going to look at here. So we have this curve, f of x, which is negative a third x squared plus 2x plus 5. And what we're going to do is take a look at it between 1 and 7. So what that means is that I'm going to not look at anything over here and not look at anything over here. We're just looking at this part in between. And what we want to do is we're going to subdivide the area into rectangles of length 2. So what that means is I'd go from 1 to 3, like so. But I'm going to stop that rectangle right there. The next one's going to go up here, go over 2, and come down. And our last one is going to come over and then come down. So I've got rectangle 1, 2, and 3, which are estimating what we have here. Okay? So we can say that the integral from 1 to 7 of fx dx is going to be approximately 2, because that's our width, times the height, which the height of that first one there is f of 1. Okay? Plus the width of our second one times the height, which is f of 3. Plus the width of 2 times the height of this last one here, which is f of 5. And then we're going to work out what all that is. Now, if we want to, obviously we can pull out this 2 as a common factor as well, and then simply do this. It doesn't really matter if you choose to do this. Obviously, when there's algebra, we can do it or not, based on whether it kind of helps us simplify things. All right, so in this particular case now, what I'm going to need to do is put this into my calculator. So I'm going to plug in f of 1 into here, plug in f of 3, plug in f of 5. And when I do all of that, it takes us quite a time. Pause it if you want to give it a chance, but I've already done it, and your answer would be 42.667. Okay? Now, we don't have units, so we don't need to say anything, but we could say units squared if we're, trying to be picky or worried about it in any way. So let's try this on a couple of more examples here. So now what we're going to do is we're going to do this one here from 1 to 7. But this time what we're going to do is we are going to use length of 1 for our little rectangles. So that means that my rectangles are going to be skinnier now. And it's probably pretty easy to kind of start to get the idea here that this is going to be more accurate because we have less that is outside of the actual graph and less that we missed on the inside. So this will be much closer, or a much closer representation. So now we're going to do the integral from 1 to 7 of fx dx. But this time it's going to be a width of 1, and let's go to that simplified version, and it's going to be f of 1 plus f of 2 plus f of 3. Now, you might say, where is he getting these from? Remember, what I'm doing here, f of 5, I need one more, f of 6. Couldn't quite fit it in there. What we're doing is we're just looking at like the height, and we're taking the height based on the left. That's why we called this a left-hand Riemann sum, okay? Because we're taking the height based on the left side of the rectangle. So then again, we're going to put all that into our calculator. Go ahead, take a minute, and you'll see that it is 41.667, okay? So that allows you to see that we are a little bit different. We had 42.667, now we have 41. And as we can kind of assume, this is probably more accurate. So logically then, if we switch to length of rectangles that is 0.5, it will be even more accurate. So now we're going to get rectangles that are in here like this, where they are even more accurate than they were before because we have even less wasted parts that are outside of our graph. Unfortunately, it does take a long time to draw these, and so this is where we end up with a bit of our dilemma, right? Or do we be more accurate and take a long time to draw all of these things and subsequently also calculate them out? Because now when I'm trying to write these out here, right, this is going to be approximately equal to 1/2 for my width times all of the left-hand sums. Or do we go with something that's easier to write, but it's a little bit less accurate? And that is that dilemma. So here, this one, like, I'm not even going to try and write all of these out because it's going to be too much. But it would be like f of 1 plus f of 1.5 plus f of 2 all the way up until we get to the last one here, which would be f of 6.5. Now, again, you can put that into your calculator, confirm that you're doing it correctly. So go ahead and pause it if you want to do that, but the answer should be 40.917. So you can see I'm basically narrowing in on an answer. If you've ever done squeeze theorem, that's kind of what we're doing here, is we're squeezing out an answer that is more and more and more accurate at all times. Okay, so let's switch over here. Let's look at the same graph, but this time we're going to look at it as though it is a right-hand sum. Okay, so our rectangles are going to be the same, but we're going to draw them based on the right. So we're still going from 1 to 7. That hasn't changed. But now I'm going to start over here at 7 and draw that first rectangle. Then I'm going to go from 5, draw it over to 3. And then from 3, I'm going to go over to 1. So you can see it looks definitely a little bit different. And we're going to get another answer. And we can guess that this is probably going to be less accurate. We can also guess that this is going to be an underestimate, right? Because there's all of this stuff that we're missing with only this little bit above that we shouldn't be including. So this should be an underestimate, okay? And so when we do this, this is going to be 2 times our f of 3, because this time we're using the right-hand sum, plus f of 5, plus f of 7. So you'll notice the difference there is that I didn't start at 1, but this time I had to start at the right-hand side. So if you prefer, you can write f of 7, f of 5, f of 3 in descending order. It'll give you the same thing. Once again, pause the video if you want, put that in your calculator, and you'll get that this is 34.667. And we know that this is an under approximation based on what we can see there. Now, as we get closer, it's a little bit harder to see, but there are still ways for us to do it. So once again, now we're going to switch it over, and we're going to do width of 1. And so we're going to draw these in, giving us only a width of 1 this time, and still going all the way over. And you can see there's a much better representation, but probably still an underestimation. So we're going to do the integral from 1 to 7 of fx dx. And this is going to be approximated by our width, multiplied by all of them. So let's do it in that reversed order I mentioned. F of 7, f of 6, f of 5. These are all of my heights of the rectangles plus f of 3. One more, can I fit it? F of 2, sort of fit it in there. But basically, we're just going to each one. We don't need f of 1 because, of course, it's a right-hand sum. So the one that's f of 2 takes us to 1. All right, and again, pause the video if you want to put that in your calculator. Check it out. It does take quite a bit of time, which is part of why I'm not doing it on camera here. And we get 37.667. So it's more accurate, but still an underestimate, most likely. Actually, it's not most likely about it. You can see it's an underestimate. All right, now, again, we're going to try this one more time, but we're going to do it with even smaller ones. So once again, we're going to do it with the halves, which is annoying to draw. So let's draw those in. Oh, man, these are just brutal to draw. Hopefully, you're doing a little bit better job than me here. Just drawing all of these in. And you can definitely see here that I am doing something that is clearly more accurate. But we can also see that it is pretty painstakingly annoying to draw as well. And if we're looking at it, again, going to be closer, but still an under approximate because there's more parts here on this side that we are not including than the parts that we included that shouldn't have. Okay, so our integral from 1 to 7 of fx dx, and again, this time I'm not even going to try and write them all out, but it's going to be 1/2 for our width multiplied by all of those heights. So our heights are going to be, we'll start over here, sure, f of 7 plus f of 6.5. All the way down until we get to this last one, which would be f of 1.5. Okay? And again, if you do that into your calculator, which is annoying, it is painstaking, we will get 38.917. So we can see that we are getting closer and closer and closer. All right, and again, an under approximation for this. So before we continue, what inferences can we make about the approximation lengths as the rectangle, the width of the rectangle decreases? Well, as we've kind of been mentioning as we've been doing these, right? What that really means is that as they get smaller, we get a more accurate representation. So as width decreases, i.e. more rectangles, we get a more and more accurate representation of the approximate area. Graphically, why do we suppose this is? Well, there we go. Graphically, this is because the smaller the width of the rectangle, the less, let's call it overage or underage. Not that these are real terms, but basically the less stuff we're including that we shouldn't for overages, and less underage, not including parts that we should. So if I'll highlight that afterwards, but underage area, you seem to have outside of the region bounded by the curve and the x-axis. So let's just quickly highlight that a little bit so you can kind of see what I'm referring to there. So let's talk about this. We'll talk about the underage as being kind of like all of these little pieces here, where we're not including this even though we should. And then the overages, right? The overages are going to be these little tiny pieces that are like there, where we included them and shouldn't have. So we're getting less of those with smaller shapes. All right. So as we keep going then, what we're going to try now is what's called a midpoint representation, okay? So we're going to start with units of 2. We're going to go from 1 to 3, but instead we're going to take our height based on the middle point, so height of at 2. Then we're going to do our height based on 4, and then we're going to do our height based on 6. So you can see here that this is helpful because the area that we missed is roughly equal to the area that we included and shouldn't. So it definitely helps us be a lot more accurate. And so our integral from 1 to 7 of fx dx can now be written as 2 for our width times f of 2, because that's the midpoint, plus f of 4 for the middle midpoint, and f of 6 for this midpoint on the last one. So then you're going to put all those into your calculator. This is our most accurate one yet in many ways, and we've got 40.667. Now, if we want to do the same thing, but go to length of 1, don't worry, I'm not going to make you do 0.5 this time, then we're going to do the same, but we're going to get our midpoints from like 1.5, from 2.5, from 3.5, 4.5, 5.5, and 6.5. And you can see that again, this is what we talked about before, where the overage and underage are much similar, but there's even less of them. So we're getting more and more accurate always when we have smaller widths. Now, I'm not going to write out this whole one this time, but this would be a width of 1 times, and our midpoint is now giving us our height. So 1.5 plus f of 2.5, etc., all the way up to f of 6.5 for the last one. And when we put that all into our calculator, again, pause it if you want to do it, but that would be our answer. So we're getting something closer and closer and closer to what we need. Oh, I did make you do, no, I didn't make you do the halves. I did not. Okay. So, all right, so we've done left-hand sums, right-hand sums, midpoint sums. The next progression is going to be trapezoidal. Now, if you don't remember what a trapezoid is, I don't know, pause the video, look it up, or wait a second. So what you might need to remember, or hopefully you just looked up then, is that the area of the trapezoid is 1/2 times the height times the two other bases put together. Or if you prefer, 1/2 times the base times the average of the two heights. Either way will kind of work. All right, so we can use that then to find these. So let's start off by doing them with the height or the width of 2. So we're still going to go over here. But now what we're going to do is we're going to be looking at making both of those heights accurate. So we draw it in like so. All right, so then we get our 3 different trapezoids. Now, of course, because the formula for a trapezoid is a little more complicated, this also means that the formula for adding them all together is a little bit more complicated. So what we're going to do here is we're going to have 2 times 1/2 times, the 2 is the width, sorry, that width there, times those 2 lengths or heights or bases, whatever you want to call them. So in our case here, that's going to be f of 1 plus f of 3. Then we're going to go 2 times 1/2 for, of course, the width times 1/2, which is going to give us the average of the next ones, which is our heights of f of 3 and f of 5. And then the width of 2 times 1/2 to give us the average of f of 5 plus f of 7. Now, the nice thing is here, in this particular case at least, is that that 2 and the 1/2, they cancel out. And so what we can do is we can kind of pull those all out front, which would be like 2 times 1/2. And then we're going to get f of 1 plus f of 3 plus f of 3 plus f of 5 plus f of 5 plus f of 7. And so what you'll notice is that the 2 endpoints are only counted once, but all the rest of them are actually counted twice. All right, so we could even simplify this formula a little more. We're going to get our width multiplied by 1/2, and then what we're going to do is we're going to say f of our 2 endpoints, so f of 1 plus f of 7, plus 2 times, and then this would be f of 3 plus f of 5. Basically, all of the ones that are not endpoints are what's going to go there. So once we've done that, again, we're going to put all that into our calculator, which is a little bit annoying. Pause the video if you want to give it a try. Otherwise, you can trust me because I did it ahead of time. And we get 38.667. Now, obviously, just like before, if we take our trapezoids and make them with a narrower height, in this case, or width is what I would prefer to call that, then what we're going to do is get something that is just like before, more and more and more accurate as we make smaller and smaller widths. Because as you can see here, I am not missing very much at all. There's very little that I'm not actually including in these trapezoids. So to write that out again, it was the integral, that doesn't look right, there we go, integral from 1 to 7 of fx dx. And this time it's going to be 1 times a half because our width is 1. And then we're going to kind of do that other one that we had talked about. So like f of 1 plus f of, and our 1 at the end there is 7. And then what we're going to do is say plus 2. This is still, maybe I'll change that bracket so it's easier to see. There's a big bracket here around everything. 2 times all of the ones in the middle there, which was f of 3, f of 4, f of 5, and f of 6, like so. Then we can put all that into our calculators and we get 39.667. So we are, again, narrowing it down more and more. And just to be clear here, in this particular case at least, this is going to be an under approximation because they are underneath it in all of our different trapezoids. Okay, so here's where we're going to need to do a lot of scrolling, or I've got them written down. So with our left-hand Riemann sums, our approximation was 42.667, and then it was 41.667, and then when we did it with a half, we got 40.917. Okay? Now for all of those, we had said those were over approximations. Every single one of them included too much. When we switched to the right-hand ones, when we had a unit width of 2, we had 34.667, 37.667, 38.917. This is just me copying all the data we just did. And for each one of them, we had said it was an under approximation. There was less, we included less than we actually needed to. Then we went to our midpoints. We switched it, and our width of 2 was 40.667. And we went to width of 1, we got 40.167. And we had said for both of those, they were harder to see, but they are still a little bit over, but much less, okay? These were less than before. All right, then we went to our trapezoids. The trapezoids in this case were under in both cases, as we just mentioned, since they were the most recent. And we got 38.667 and 39.667. So if these are both under, and then we had an overage, the things that are going to be kind of the most important to us are going to be this one and this one, because that means that our actual number is going to be somewhere in between those two. All right. And what we're going to do, we'll come back to this later and kind of see exactly how close or accurate we actually were with these. So let's try practicing this on a few questions here. So given the table of values here, we're going to basically approximate each of them using a Riemann sum. That's really hard to see, so I'm going to zoom in a little bit. There we go. Much easier to see now. And so here we're going to be approximating it from 0 to 25 using midpoint with 3 intervals. So if we have 3 intervals, that would mean we're going to go from here, right? 0 to 7, 7 to 15, 15 to 25. And we're going to use the midpoints, so we're going to use these ones that are in the middle as our heights. So the approximation from 0 to 25 of fx dx can be approximated by saying the width of 7 times a height of 6, because that's our f of midpoint, f of 4, plus, this time from 7 to 15, we had a width of 8, and we had a height of -10. And then for our last one, we had from 15 to 25 is a width of 10 and a height of 8 being that midpoint. So if I put all of those things together, let's see. Well, these ones are going to cancel out because they're positive 80 and negative 80, so we just get 42. So our last 3 examples, this one we're going to go from 0 to 15 this time, so we're not going to go all the way across. So what that means is that we're not even going to include these ones here. And we're going to do left-hand Riemann sums with 4 sub-intervals. So on our intervals, we're going to look at 1, 2, 3, and 4, and then we're going to use the left-hand side to figure out our height for each of those rectangles. All right, so from 0 to 15, the integral of fx dx can be approximated by that first one is going to be a width of 4 times a height of 15, because I'm using the left-hand sum. Plus, then I'm going to do from 4 to 7 is a width of 3, and our height at the beginning there on the left is 6. Plus, our width from 7 to 12 is 5, and our height is -5 there. And then our width from 12 to 15 is 3, and our height is going to be -10. Then if we put all those things together here, by putting them into our calculator, we got -30, -25, -55, 60, so that's 5, 18, 23. Okay, use your calculator if you have a hard time doing that. All right, next one here, we're going to go this time from 4 to 20, which means we're not going to include this one or this one because we're only looking from 4 to 20. We're going to use right-hand sums, and we're going to do, once again, 4 intervals. But this time, we're going to take our heights based on the right-hand side. So the integral from 4 to 20 of fx dx can be approximated. Doesn't matter which one we start at. Let's go here. Our width is 3 from 4 to 7. Our height, though, is not 6. It's -5 because we're using the right-hand side this time. Then from 7 to 12, that's a width of 5 with a height of -10. 12 to 15 gives us a width of 3 with a height of -2 on the right side. And then from 15 to 20 is going to give us a width of 5 and a height of 8. Putting that all together here, we're going to end up with -31. All right, last example here, what we're going to do is we're going to use trapezoidal. We're going to go from all the way from 0 to 25. We're going to use 3 subintervals. So we already kind of did this one where our intervals go from 0 to 7, 7 to 15, and 15 to 25. However, as we know, when we're doing these, the equation for this is a little bit harder because the trapezoidal area is a little harder. So the integral from 0 to 25 of fx dx can be approximated by our first width there is going to be 7, and then it's going to be times 1/2 times the 2 heights added together. So in this case, it's going to be 15 plus -5. Our next one in the middle there is going to go from 7 to 15, which is a width of 8, height of 1/2. We're going to use the 2 heights added together, so -5 plus -2. And our last one goes from 15 to 25, which is a width of 10. It's going to be then times 1/2 because we're averaging, and our 2 heights are -2, oops, should be -2 plus 20. Then we can put all those things together. So at that point, you can go ahead and put that into your calculator, and you'll get an average of 97. So that'll be it, guys. After that, you can go ahead and do the practice problems and move on from there.